So, here we go. This thing is a little bit... Oh, the wire's on there. Wires. There we go. Now we're good. Okay. We've been taking a lot of time trying to explain the whole project, the whole problem of that darn ball going up in the air and analyzing what it is. I've tried to give you history from Descartes and Newton as it goes on to hopefully have you have some sort of connection to it. Today we're going to wrap up the whole thing, and we're going to start our next unit, which is going to be, we're going to spend about 3 weeks just doing all limits. Okay, that's the very next chapter that we're going to do. Then we're going to come back and we're going to do more about this whole derivative thing when we finish the limits. So just be aware, this was background on the big picture for all of the whole first semester, which is all about derivatives. And we're going to take a break from the laying the foundation to go solely on limits for a couple of weeks, and then we're going to come back to derivatives, and that's what we're going to spend the whole rest of the semester on. Okay, so I've tweaked the project, my little Desmos thing here, so that it only includes the times from 0 to 8, and then I put these roaming dots on here. So can anybody tell me what each of those coordinates tell us? Everybody look at it, focus on it, get mesmerized by it, and then I'll call on somebody to explain what do those things mean. To the untrained eye, it looks like there's just some stuff going on there. It's a cute little animation. But you guys are going to be better than that. You're going to be trained calculus reviewers of graphs and understand what goes on. So, Kendra, what do you got?
The x on both of them is the time. The y on the red dot is the velocity. And the y on the green dot is the height.
Couldn't have said it better myself. Excellent. I'm going to just repeat it so everybody hears. The x coordinate for both of them, you see that are the same. That is the time from 0 seconds to 8 seconds and back again. The y coordinate on the blue one is the position. It's the height above the ground at any given moment. And the y coordinate on the green one is the velocity of the ball at every given moment. Does that make sense? Okay. You have to see what this is. Now, just to give it to you straight out, the blue one is the position function, and it tells you how high you are above the ground at any given time. The green one is the derivative of the position function. It's the derivative of the position function, and it produces the velocity. So it's called the velocity function. Okay? And we can state instantaneous velocity and instantaneous position throughout the whole flight. Okay? If I put the slope on here, which was this one, this is the connection. You have to see this. The slope of that purple line changes throughout the whole time, and it's the slope of the line tangent to the position function. The slope of the purple line is the y-coordinate of the green one. The y-coordinate of the green graph is the slope of the purple line. I'll freeze frame just a couple of spots to clarify it. So if I say, let's pause it right here. See the red dot? The red dot is the actual 0, 128. 128 over 1 is the slope of that purple line right now, 128. If I pause it here, the slope of the purple line is 16. It's 16 over 1. If I stop it exactly at 4, the slope of the purple line is 0. And continuing on, here the slope is negative. It happens to be negative 48. And if I go all the way down to the end where it's at 8, then it's negative 128. Yes, ma'am. Say it again. The green line is the velocity function. We talk a ton about a position function, a velocity function, and then an acceleration function. Those three functions give us the position, the instantaneous position or velocity or acceleration at any given time. All we have to do is plug a time in, and bam, we get those values out for whichever function that we have. Calculus is all about finding the derivative of a function. The first semester of calculus. Okay? We developed the very first one yesterday using the definition of the derivative. And it took a long while, didn't it, to do that? It was all this complicated math. Okay? We're gonna hopefully you guys will recognize some possible shortcuts, or otherwise we're gonna have to do that for every single function that we have for the whole year. And that could be bad. So I'm depending on you. So here we go. Really quickly, what we discovered yesterday was this is the function for our ball that was in the air. Then the velocity function for our ball came from what is called the derivative. And the notation that we use here is S prime. This is the derivative of S of t. Okay. And it came from this limit as delta x approaches 0 of S of x plus delta x minus S of x all over delta x. This is the only way that Newton figured out how to find the derivative at a point, meaning how to find the slope at a single point. Because you can't do it unless you have 2 points. So he had to invent a new way, and he invented the limit process. Now we cranked this whole thing out, blah, 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 yesterday, and we ended up with something like the limit as delta x. Give me the second to the last step. It was maybe negative 32t minus 16 delta x plus 128. And we were supposed to find this. And then the bell rang right around this point. So we had to finish up really quick. Oh, yes. This is an x here. Thank you. See, that's good. That's the kind of stuff that you got to catch. And I like that when you do that. So this is the thing that we're going to spend a lot of time on now, and that's actually finding the limit. The way that it works is we're going to let delta x get really, really super close to 0. Meaning, look at this. If I take a number that's really super small, really super close to 0, think of it like as 1 millionth or 1 billionth or 1 trillionth. And you multiply it by 16, what is the result of that whole thing? It's still really small, isn't it? So this becomes actually insignificant. Okay? The trick is we don't let it actually equal 0, but we let it get super, super, super close to 0. So it just sort of like goes away. So that means that when we take the limit of this thing, this expression, what the answer is negative 32x plus 128. And this is what's known as the derivative. Because after we've taken the limit, this part here becomes so insignificant that we can just ignore it. Even though it's not actually become 0, it gets really, really, really super close to 0. So the derivative of s is negative 32x plus 128. S was this. Okay? Look at the front. Look at this. Which graph is that over there? This one. That's the blue one, right? That's the parabola. Which one is that? It's the green one. Okay? We just created the velocity function from scratch using Newton's method. Okay? And hopefully we can figure out better ways to do that to make it go a little bit faster. Anybody notice anything about those two? Just curious. Think anything you learned last year? Is that my phone? Well, now it's going to be too late. I won't be able to get it. See, you only get 3 rings. So, all right. Anything from last year? Just curious. 16 times 2. 16 times 2, or how about negative 16 times 2 is negative 32. And then you just drop that t. It's in there somewhere. Okay? All right. You learned the fast way to do it last year, and we're going to do that after we do our limit chapter. Okay, so we're going to do that. But I wanted to show you from the ground up how this actually came about. Okay, now we're going to toss all this aside, draw a big line on your notebook, and we're going to start our brand new unit. You hate the Swivl?
No, like I'm not going to be here tomorrow, so someone has to send
Oh.
it. Well, Adam's going to be gone, so there has to be
Yeah, there's going to be a lot of people gone, banned.
because Evelyn's gone.
All right, somebody needs to take over for Megan.
It's really easy. I'll do it. Maybe do it.
Okay, so Libby,
Chuck it out of the window, though. Okay. I don't know what to do.
she'll teach you. Okay. The limit of a function as x approaches some number is the, I'll put this in quotes here, expected value of the function as x approaches, is approached, I should say, or as x approaches the number from both the left and right. It's a very verbal way to say it, and then we're going to explain what the heck that means. The limit of a function as x approaches some number is the expected value of the function as x approaches the number from both the left and the right. Okay, you've touched on limits before a little bit last year, so let's recall what this means. Shoot, I got to scroll this up just a tad so you can see the bottom. And okay, I guess we're good here. So we're going to express a limit here as x approaches 2, and I'm going to explain what this means. The limit as x approaches 2, this is g of x, so I'm going to say of g of x is equal to 4. The limit as x approaches 2 of g of x is 4. Look at that picture. Okay, let's go to the definition of what the limit is. Okay, what is the limit? The limit of a function as x approaches some number is the expected value. Okay, as of x, as we approach x from both the left and the right. So let's approach x equals 2. This is what I'm approaching. I'm approaching x equals 2. So down here, I'm going to say, all right, I'm going to approach x equals 2 from the left. Okay, when I do that, I'm looking at what the expected y value is. So at 1, I'm like up here. And as I get closer to 2 from the left, the corresponding y values are coming in here. So if you would say, hey, what does it look like the y-coordinate is going to be as I approach x equals 2 from the left, it looks like the answer is going to be 4, doesn't it? Okay. The key word here is the expected value. Okay, then we're going to approach, you have to approach from both sides. So now I'm going to approach x equals 2 from the right side. And as I do that, I'm going to plug in these x values. I'm going to get closer to 2. And I'm going to look at the y-coordinates. So as I approach x equals 2 from the right side, I get these y values. And if I get really close, but then I say, I'm not allowed to go there, what is the expected value as x approaches 2 from the right? And again, it looks like it's 4. Okay? If the left expectation matches the right expectation, then we have a limit, and we say that that's what the limit as x approaches that value is. Okay? And so the answer here is 4. Anybody wondering, well, what's with that 6 then? Right? How come the answer is not 6? Well, look at the definition. It's the number that it's expected to be. Okay? This goes back to the reason why I explained this. Look back at that back wall. Remember that whole thing about that we can't have a slope with a single point? So we said, we're going to let this delta x get really, really close to 0, but we can't let it equal 0 because originally it would make the whole thing blow up. But we're going to let delta x get really close to 0, and we see that this part becomes insignificant. But we're not allowed to let it equal 0. You see? This is the reason why we don't actually care what happens when x equals 2. We don't care. We just have to say, what does the expected value look like it's going to be? And if we come in from the left and we come in from the right and we get the same answer, then bam, that's the limit. Make sense? Okay, we're going to do a couple more. So, here's another one. Okay, I have some function. I'm going to call this function h of x. And I'm going to focus on what is the limit as x approaches 3 of h of x. Okay. All right. First things first, we got approach from both the left and the right. So, tell me, what is the limit as x approaches 3 from the left? What do you say? 1. If you were thinking 1, you are correct. Okay? Because as I'm approaching x equals 3 from the left, it looks like the answer is going to be 1. That's the expected value. Okay? As I approach x equals 3 from the right, again, look at the definition. What is the expected value? What does it look like it's going to be? As I approach here, what is the limit as x approaches 3 from the right? What'd you get? 4. If you said 4, you are correct. Okay? Because if you follow here, it looks like the next logical value is going to be 4. Okay? So now, write this notation down if you haven't been doing it. If this is good notation for you. What we're going to say is the limit as x approaches 3 from the left, this is a little minus sign up above the 3, of h of x. The limit as x approaches 3 from the left of h of x, what did we say that was? That was 1. And the limit as x approaches 3 from the right, little plus sign here, shows that it's coming in from the right side of h of x. What did we say the answer was there? We said that answer was 4. Okay? If these two match, we have a limit. If they don't match, we say the limit does not exist. The limit does not exist. What show? Mean Girls. Okay. So we say does not exist. And watch this. We're going to put a because in here. Because the limit as x approaches 3 from the left of h of x does not equal the limit as x approaches 3 from the right of h of x. That's the reason why the limit does not exist. Does not exist. Exits. Exits. Sometimes I just get so excited. My words. So the limit does not exist because the limit as x approaches 3 from the left does not equal the limit as x approaches 3 from the right. Okay, that clear? All right, so now let's take a peek at some other ones. Okay. All right, so I'm going to ask a few questions here. So I see a x equals a, and x equals b, and x equals 0, and x equals c. Okay, so this is a, b, 0, and c, and let's call this f of x. So 4 questions. You're going to answer all 4. Limit as x approaches a of f of x equals limit as x approaches b of f of x equals 3. Limit as x approaches 0 of f of x equals, and the limit as x approaches c of f of x equals. Get 4 different answers. Compare your answers with the people around you. And I'm going to call on people to justify what the answer is and then give a reason for why it is what it is. Smile, Bitsy. See, I gotcha. Little helper thing on those. Okay, once you get an answer, start comparing. Okay? I want to hear arguments, justifications. Are you making faces?
What?
Are you making faces? Oh. You're in this. You're in this all the time.
I know. So for that one, it is and then zero. I was thinking asymptote right on it. Yeah, make sure that's 0.
Okay, have you come to 4 conclusions? Okay, volunteer for the first one, number 1. Volunteer, you're going to fill in the blanks here. Come on, come on, come on, come on, come on.
I'll do 3.
You get to grab a marker and go.
Do it, Harry.
Come on. All right, Harry's going to do it. Volunteer for number 2. Volunteer for number 3. Here we go. And volunteer for number 4. Looks like nobody. We need 2. Okay. And remember, I don't care if you get it wrong.
I care. Everyone else. I care.
We have to get over that. You see, it's more important that you try and fail than to
Have you done
not.
graduation speeches?
Yeah, I did it last year.
Did you do any before that? That's terrible.
Yeah, I did one a long time ago. Yeah, they handed cookies. Were you there? Yeah, you had. Of course, you were there. That was pretty fun.
It's giving me proposed board.
I have no idea if that's right.
I just write NA in my notes because it's like
Yeah. On the AP exam, you'll see it as does not exist.
just in my notes I estimated it. That's just how I wrote it.
That's the one where I said I have no idea.
Because it was the second semester, it's not like testing, it's technically semester stuff. But she wanted to test for
Okay, let's see what we got here. I think maybe I'll go up here and we'll reference what we have here. Everybody look at the graph as x approaches a. As I would see this, as x is approaching a from the left, the y values, okay, the y values are going down to negative infinity. And that is correct. Top one is good. As x is approaching a from the right, these y values are going up towards infinity, so positive infinity is also correct. Okay? And so, do those two match? No, they do not. Therefore, the limit does not exist. Thumbs up to Harry. Okay? Number 2. Number 2 is as x approaching b. So, as x is approaching b from the left, it looks like the answer is going to be 1. That is correct. As x is approaching b from the right, it looks like the answer is going to be 1.5. Do they agree? No, they do not. Does not exist. Kayla, was that you? Yeah. Kayla, very good. Number 3. You can stand. Number 3, as x is approaching 0 from the left, it looks like the answer is going to be negative 2.5. Good. As you approach x equals 0 from the right, looks like the answer is going to be negative 2.5. Do those equal? Answer is yes. That's the great question. The expected value. This is one of those times where we just don't care what happens at that point. And it goes back to Newton's thing that I was trying to explain, that we're going to allow delta x get really, really close to 0, but we can't let it actually equal 0. Okay? So you have to break the habit. This limit is a new idea. I'm not asking you. If I said, what is f of 0? If I asked that question, what's f of 0? Your answer would be 1, because it's right there. Okay? But when you ask the limit question, I'm not asking that. Yes?
So does that mean our velocity graph is what we expect and not exactly what we know?
Yeah, it's so super close that it is exact. Close enough is what it is. Okay? And it's the power and the limit is what does it. Okay? So, all right, very, very good. So that's that. And the last one, as x approaches c from the left, is 2.5. As x approaches c from the right, looks like it's 0 or maybe a little bit above 0. Okay? And then do those equal? And the answer is no, so that's that. Okay? How many people got a grasp? Never, forgot about that. Very good. Got a good handle on that? Okay, I'm going to give you one more. Okay. So we're going to approach 3, -2, -1, and 0.75 and 2. Give me the answer for each one of those limits.
What do we call this one? Is it still f of x?
Z of x.
Yay!
And this you can't see it, but it does hit right there. Which one? Yeah, these are both approaching your picture of that. Yes? 0.75. Yeah. Some value there. Oh, you are awesome.
Did you see her graph paper that she tapes?
Yes.
To her butt?
Like, I do that with all of them.
She.
She does not deserve to be called.
Yes, she does. This is gold medal worthy.
Here, when she did it and what show she watched before.
Did you watch The Big Bang Theory?
No, she watched Teen Wolf.
She doesn't deserve that. She needs to be sleeping.
Okay. Hurry up.
I fit it all in here.
Are you doing the positive two?
Nope. Yeah, we're doing the positive 2 and 3 here.
Oh, it's right there.
It also could have been since I don't think I would ever
Like your spin.
I do.
But this is happening in weeks. You start out with and down. Next time you don't hang out with
Okay, we're going to practice vocabulary and wording now. Shh, shh, shh. Okay, who thinks that they have the answer to number for the first one as x approaches -3? Raise your hand. Somebody who we haven't heard before. Okay, Megan. Limit does not exist. Okay, correct. Now, can you say it with the wording that I've said here? For example, the limit as x approaches -3 from the left. So give me both those answers.
Okay, so when it's approaching to the left, it's -0.9.
Okay, Summer.
And then when it's approaching to the right, it is a different number.
It's a different number.
I can't
Estimate it.
like 0.7.
Okay. Now say it in the right way.
Wait, as in going to the right?
Yes. Both of them.
As it approaches as x approaches -3 to the left, it is. What? The limit as.
Got the limit.
The limit as x approaches.
So I'll just go right back.
The limit as x approaches -3 from the left is
-0.9.
of the function, yeah. And then the limit as x approaches -3 from the right is. Okay, so that's the deal there. All right, we're going to run out of time on this. So what'd you get for 2? 0 is correct. Next one, infinity. Next one, -1.9-ish. Answer the last one? -0.5. Okay, everybody look at here, page 54, due Monday, and we're moving on tomorrow.